Today we're going to be doing u-substitutions that result in inverse trigonometric functions. So we're going to use these three formulas, and notice that this one right here involves the arcsine, this one involves the arctangent and arcsecant, and their forms are quite different. When you have the constant, a is a constant, so you're going to have a squared as a constant. We have the constant first and then a function of u squared, or a function of x if you want, squared. That will result in an arcsine. Now, if you happen to have the u first and then the a squared second, you also have to have an extra u here, you're going to have an arcsecant. And if you have a sum, you don't have any square roots, and you have a sum of squares, then that's going to give you an arctangent. Now, you may wonder, why do we not have our cosine, our cotangent, and our cosecant? But if you go back and check the derivatives of those functions, they're just going to be negatives of the ones that we already have. So that would be superfluous to list those. There's no need for that. One more comment about inverse trigonometric functions is that in your book you may see it written as this, for example, sine inverse of x. This inverse represents to a inverse function, so inverse in terms of composition of functions, not multiplication, because some people may think about it as 1 over sine x, and I'm writing that not equal to, because this one is called cosecant. And the confusion comes from the fact that we usually, whenever we have powers of a trigonometric function, we write them here. This means sine x times sine x. So the operation here is multiplication. And when we put it here, to be consistent with this notation, this should represent the multiplicative inverse, but it does not. It means the inverse function with respect to composition of functions. So that is where the confusion comes from. So it's very, very reasonable. That's why instead of writing this, I prefer to write it as arcsine, because that reminds you that it is a completely different function. It's an inverse function. It is not a reciprocal, a multiplicative inverse. So I like to write it that way. And that is much more in line with what we do with, for example, e to the x and natural log of x. We don't write it as e to negative x, because that certainly is a multiplicative inverse. So I just like to write arcsine, arctangent, and arcsecant for these. It's going to take us a little bit extra to write them, but I think it's worthwhile to avoid confusion. All right, so let's get ahead and get started with one of these problems. So let's do an easy one to start. So for example, let's do the integral of, I have to change to a pen. So the integral of e to the x over 1 plus e to the 2x. I'm going to keep it simple for the first one. Well, some of you don't like exponentials, so you may think, well, that's not the simplest to start. But the reason why I'm saying it's simple is because the substitution will become clear when we look at it or write it a little bit different. Instead of writing e to the 2x, I'm going to write it as e to the x squared, because that, you see, whenever you have a power to another power, the exponents multiply, or in this case, e to the x to the square, or to the power of 2, becomes e to the 2x. And of course, don't forget your dx. And now that looks a lot like this one right here. So we're going to try to convert it into that. So u seems to be one of those factors, so u would be e to the x. So for this section, what you're going to try to do is look at the formulas you have and see what your integral already kind of looks like. And you're going to try the substitution that is the one that your formula suggests. So in this case, you get that du is e to the x dx. Remember, the derivative of e to the x is e to the x itself. So you notice then that this right here becomes right away your du. So with that in mind, then you can just have that this is du. I'm going to put it here in the numerator. I can put it 1 and then put the du over here. That's the same thing. Some people don't like that, but it's the same. So here you get u squared. And so this is exactly the formula that we had for the arctangent, if you go back and look at it. So compare this one to the one we have. Well, a would be 1, because we have 1 plus u squared. So a would be 1, so that integral will become just the arctangent of u over 1. So just arctangent of u. Let's delete that little box because we're going to be using all of them, or try to use all of them anyways. So this just becomes the arctangent of u. And now we take back our substitution, and that's going to be the arctangent of e to the x plus e. All right, this one will not require much of a, if any, actually no u-substitution. We're going to use the formula that we were given directly, because this becomes 9 integral between -3 to 3 dx over 9 plus x squared. And maybe this 9 would be a good idea to write it as a 3 squared, so that our formula looks exactly what we had above. So let's go look at our formula. Sorry, I didn't mean to zoom, I just meant to scroll. You see a is going to be 3, because you have 3 squared plus x squared. So u equals x and a equals to 3. So let's substitute in, would be 1/3 of the arctangent of x over 3 plus c, but we're going to have we have a definite integral, so we're going to go ahead and do that. So we get 9, that goes along for the right, and remember we had 1 over a, is going to be 9 over 3, arctangent of x, which is our u, over, so it was u over a, so x over 3. All of it evaluated between -3 and 3. So that's 9 over 3 is going to give me a 3. And then I'm going to have the arctangent. Now when I evaluate at 3, this is going to be the arctangent of 1. Arctangent of 1 is pi over 4 minus the arctangent of -1, which is -pi over 4. So this is going to be 3 times, and this you can look in your unit circle, or you can plug in your calculator, but the calculator, or most of them, won't give you an exact value. They're going to give you an approximation, so it's better to do it on the, look at it on the unit circle. So pi over 4 minus negative, so that becomes plus pi over 4 again, which is going to be pi over 2, so this becomes 3 pi over 2. All right, so if you look at this graph, this is roughly what it looks like, and I debated whether to copy paste something from like a Desmos or something, but the graph is good enough, and I think I did a decent job. So the graph would look like this. This is the graph of, and I forgot to write that, y equals 9 over 9 plus x squared, and the area that you'd be computing is this area under this curve between -3 and 3. So that area happens to be 3 pi over 2. All right, we'll do another one of these problems, but this time let's do something that doesn't involve the arctangent, maybe something that involves the arcsine. Okay, so let's take a look at something a little bit funny. I don't know. I do need more space than that. So let me put a cosine here. And then perhaps a square root of 9 minus sine squared. I was going to put a 1, but 1 minus sine squared would become the cosine squared, and then square root of the cosine squared is absolute value of cosine. Yeah, not very exciting on that one. So let's change that to a 9. So that works out well. All right, so let's integrate that. And what you notice then for that one is that it looks kind of like this. 9 would be 3 squared minus sine squared. U is going to be the sine. And then whatever you have in the numerator, hopefully it's going to be your du, and it is. So let's take a look at that. Let's write u equals sine x du equals cosine x dx. Taking my derivative there. All right, and the cosine x dx, it's already the du. I already have it present in my integral, so I don't have to do much. That's just going to be du. Okay, those are the best. So I just get du, and then square root of 9 minus u squared. And then As I said earlier, you pick a to be 3 because a squared is 9. So a squared being 9 means a could be plus minus 3, but just pick the positive one. Makes your life a lot easier. All right, so the arc sine of u over a, in this case, is just u over 3 plus c. As I told you, nobody cares about, never mind. Sine over 3. Sine of x over 3, sorry. Plus c. One last one. So let's take a look at this one. And if you remember what you have here, this one looks a lot like, you see you have the function in the first entry in the square root. So it seems like we want to do, and I want to write it in detail, we want that t to the fourth really to be u squared. So if you take a square root, then you would have that t squared is u, technically the absolute value of u, but my substitution here will work as u equals t squared. So then if I compute my derivative, du is going to be 2t dt. So I can plug that in. Now, I will have to reorganize things in such way. So for example, here, I'm going to have to write my dt as, I keep moving the t to the left, then to the right, then to the left again. Sorry about that. Dividing by 2t on both sides, so du over 2t. And let's go ahead and plug everything. It's kind of confusing to have all this messed up there. All right. I hope that that's not too confusing. So we just wanted to compare to the integral we had for the arcsecant, and we noticed that t squared would have to be u squared, and then you have a t, but we don't really know what that's going to look like just yet. So we're going to plug everything in to see what happens. Now my dt is going to be du over 2t. Now I have an extra t here. I'm going to write it there because I still don't know what to do with it. I'm going to have a 1, that just because I moved my dt here to the right. You see you have dt, this is dt. So I'm going to put a 1 in the numerator just to have the fraction. And then I'm going to have a square root of, and this one we already know what that's going to be because we rigged it so that this would be our u squared minus 1. We fixed that so it would be that, so that it looks kind of like what we have here, square root of u squared minus a squared. A is going to be equal to 1. I think we'll agree with that. All right, so now we need a u here, but that's the nice thing about this du, because whenever you move this t and multiply it times this guy, I'm going to write it in 2 steps. This is going to become 2t squared. I just moved the 2 to the front. Square root of u squared minus 1. But I told you that u is t squared, so I can plug that as a u. So let's put the 1/2 out of there, and then write it as du over u square root of u squared minus 1. And we have the exact same form that we have now in this integral here. So it tells us it's going to be 1 over the square root of a. A is 1. So sorry, square root, absolute value, sorry. 1 over the absolute value of a. That's going to be 1 over 1. So just 1. And then we have, well, copy the 1/2, I suppose. We do have that. And then arcsecant of the absolute value of u over 1 plus c. So I should have just left that as a, take back our substitution. It's going to be 1/2 arcsecant of u is t squared. Now, I don't need my absolute value bars because t squared is never negative. So, I mean, these are real variables, of course. So there's really no point in writing extra absolute value bars there. So I get my, I can put parentheses if you want, I get my integral right there. All right, and that's that for this video, guys. Thank you for watching, and I'll stop right here.